Taking a look at quiz number 1 from 2014. It says rank the overall dipole moment from smallest to largest. Okay, so we have 4 structures. Let's call it A, B, C, and D. The instructions ask us to rank the overall dipole moment from smallest to largest, smallest being 1, largest being 4. So again, when we have rankings, I like to find the extremes and fill in the blanks. Here, you got to remember, we're talking about overall dipole moment of the whole molecule, not just a bond. So we got to be thinking about the molecule completely, and when we think about molecules completely, you got to think about them in 3 dimensions, right? Remember the wedges and the hatches. The wedge here means the chlorine's coming out at us. The hatches mean the chlorine's going away. These 2 H's are in the plane, and so on and so forth. So if you look at this, you probably want to look and say, well, what's different about these? So first things I started to identify, it looks like everything either has chlorines or fluorines, right? Good. So then I look at the periodic table, so what's the difference between chlorine and fluorine? Well, fluorine is above chlorine on the periodic table, so I know fluorine is both smaller and has a higher electronegativity. Right? I know those two facts about it. But I also got to remember, I got to think about this molecule in 3 dimensions, and that an overall dipole moment can be 0 if polar bonds are canceling each other out. So the trick here for one of them, I would look at and say, this has all the same things, right? So fluorine is very electronegative, and it's going to pull on this carbon, but if they're all the same, it's going to cancel each other out. So this is actually the smallest dipole moment, so that's 1. Yep. Now, if I try to look for the most polar, or the greatest overall dipole moment, I would look for the fluorines again, right? So I would say, well, these obviously have areas where H's and, I don't think hydrogen doesn't make polar bonds with carbon, right? So then I look for fluorine versus chlorine. This one has 2 fluorines, this has 2 chlorines, this is 1 chlorine. 1 is less than 2. Fluorine is more electronegative than chlorine. This is probably going to have the most overall dipole. So I'd rank that being 4. And then 2 is more than 1, 3, and 2. No, so this is not going to cancel out. It's going to create almost like a top part of the molecule pulling up while this is delta plus down.
Because they're not opposite?
Because they're not opposite, right? It's not canceling it out, right? It's a tetrahedral geometry, right? What's the hybridization state of all these carbons? sp3, because it has no pi bonds, so it's going to cancel each other out. Okay, taking a look at, this is again quiz number 1. This is number 6 from 2014. Okay. So it says draw the structure of the expected conjugate acid and conjugate base in the following reaction. Now this may look a little intimidating, but if you stop and think about what you know, it shouldn't be too hard. You know how to do this. So first, easiest thing to do is, what's the acid, what's the base? So you have an alcohol and an amine, right? Oxygen and nitrogen. I gave you the pKs, so it already should be a dead giveaway. Even if I didn't give you pKs, you still should know which one's going to be the acid, which one's going to be the base. So you know that this has a low pK, this is going to be the acid, this is higher pK, it's going to be the base. But you don't even need the pKs because you understand electronegativity. Right? If I'm talking about an acid-base reaction, usually I'm talking about a bond to hydrogen. So we have an OH bond and an NH bond. Which one's more polar, OH or NH? So which one's going to be more likely to be an acid? Because it's more reactive and more polar. Good. So this is the acid already. And if the reaction is going to take place, what must this be?
Base.
It has to be the base. The other thing I told you to do always with these structures is what? What's the first thing I would tell you to do? Not necessarily drawing all the hydrogens, but I would tell you to add lone pairs. I said that, I think. So the oxygen has 2 lone pairs. The nitrogen has 1 lone pair. Let's talk about those lone pairs. Who's holding onto those lone pairs tighter, oxygen or nitrogen?
Oxygen.
Who's more likely to use the lone pairs in a reaction then, oxygen or nitrogen? Who's holding the lone pairs tighter, oxygen or nitrogen? Oxygen holds them tighter. So who's more likely to use them in a reaction then? Nitrogen. Right.
Yeah.
These are more reactive. Nitrogen is not as electronegative. It's not going to hold its lone pairs as tight. This is a more reactive bond. And so when we draw the mechanism, we take the electrons from the nitrogen, which is electron rich, right? The lone pair is electron rich. I'm not saying that the oxygen has electrons too, it's electron rich as well. I'm not saying it's not, but it has the most delta plus site of the whole place, right? It's the most acidic, weakest bond, reactive bond right there. So I take this lone pair, snake it around here, come to sigma star, the 2 electrons in here go to that oxygen.
Why would they go to that oxygen?
Because this bond this is a polar covalent bond, right?
Yeah.
We already said this is the most polar covalent bond. The oxygen's already hogging these electrons anyways. This nitrogen comes along, takes that H, and then these electrons can go finally to that oxygen.
So in a mechanism, when you take the electrons and draw it, then the ones that you took from the base and put to the acid, which created the bond, why are we looping them?
I just loop them to show you that I'm taking both of them.
No, like the second one, you see. Like
I loop them
the
because I'm still taking, because I want to show you that I'm really taking both of these electrons and they're going there.
Okay.
I just like to loop them because I like to see the electrons move.
Okay.
So now let's shrink this up a bit. And now another term that came out of here that you're probably like, oh my God, conjugate acids, conjugate bases. I remember that being super confusing in Gen Chem. Awesome, thanks for bringing that up again. It's not super confusing because acids are electron what? Rich or deficient?
Deficient.
And bases are electron?
Rich.
Very good. So now if you just look at this reaction, who got electrons here?
Oxygen.
The oxygen did,
Because it was confused.
because it was deficient, and it got a lone pair, right? This lone pair, I'm drawing red. So now the oxygen got 2 electrons. It should have a negative charge, right? And the nitrogen formed a new bond. Oh. Right, because that's why why did I loop these 2 electrons? Because I'm showing these 2 electrons are now going to form a bond with that hydrogen. Because how many electrons in a bond?
2.
2. Yes, sirree. But I'm doing 2 now. There, and these are those 2 blue electrons now. And now the nitrogen should have, right? Did I balance my charge? Plus charge on the nitrogen. Good.
So the hydrogen with the 2 blue dots is from the OH right there.
That's right. This is that hydrogen right there.
How'd you know to put it right there?
I could put it up. I could have put it up here. It doesn't matter how I put it.
Okay.
Just as long as it's on the nitrogen.
I have a question.
Yes.
So it looks like in the reaction we actually created an acid and a base. Yeah.
So right. So yeah, great. So great. So this is why I was trying to lay it back to what I talked about in class. So this it's easier to identify these as on the. So remember, every acid base reaction is an equilibrium reaction. Notice the equilibrium arrows, right? It's a teeter-totter, right? So, right, I did create an acid and base. It's all a matter of perspective. Sometimes if I'm looking at it from this side, these are the conjugate acids and conjugate. This is a conjugate base, conjugate acid. If I look from this side, these are the right. Conjugate and all that stuff is just a matter of perspective. Which side of the reaction you're looking from. It has nothing to do with anything else. So honestly, I don't care about those terms that much. So if you were going to identify these 2 things, this and this, what would this be, an acid or a base?
Base.
Base, why?
Because it has
Because it's electron rich, right? It has a negative charge. It's a base. And would you say this is a more reactive base or a less reactive base than our nitrogen over here?
Then what?
Why? What?
It's more reactive
Why? That's right.
because it's got that extra little.
Has a negative charge, yeah. Right? Would you guys remember things about charge, right? Charged things are more reactive. All right, so this is actually a more reactive base than this one. So, what about this? What's this going to be, an acid or a base?
Acid.
Acid.
That's the plus.
Because of the plus. It's electron deficient. Where's it electron deficient at?
The hydrogen.
On the hydrogens. Right? And is this a stronger or more reactive acid than the alcohol?
No, that's
No,
reactive.
Has a plus charge,
Oh.
which
Wait,
if things have a charge, are they usually more or less
more
reactive?
because it's an acid.
It's more. This acid is going to be more reactive than this acid. This pKa is going to be much lower than this pKa. Has a plus charge. Does nitrogen want it? Does nitrogen want to have 4 bonds?
So,
No.
so if there's any charge, it's going to be more reactive than the one that doesn't have charge.
Right. Absolutely. Right. You learned that. Think about what you said, right? You learned about, are charges good or bad? You guys do, right? Usually they're bad,
They
right?
don't want charge.
They don't want charge. They're usually more reactive, right? They're usually more
Oh,
reactive. Duh,
Yeah,
right?
okay.
Good.
What is?
So this is one of the, it's like the, charge is kind of the fifth thing that affects acid-base reactivity, right? We've learned about electronegativity, size, hybridization. We're gonna talk about resonance after the quiz tomorrow. And then charge, which I assume you guys should all, we kind of know already how that affects reactivity.
So do you think it's
So this is number 8, quiz number 1, 2014. So I haven't really got to this yet, but I will. Let's see. So the question here says, why is the alkyne CH bond acidic despite having a strong nonpolar CH sigma bond? Okay, so in this case, it's highlighting essentially reactivity in one of two cases where one, in this case, is highlighting the formation of a stable product, a carbanion in this case. But this is weird because we just got done talking a lot about bond lengths and bond strengths, and we know that this CH bond is between a carbon that's what hybridization state? sp hybridized. So what orbitals are forming this CH bond from this carbon? It's a sigma bond. What hybrid orbitals is this carbon using to form? It's using just one sp orbital, right? To form this bond here, right? And sp orbitals are long, or are they fat, tall, or skinny? They're fat and short. So this should be a really stable, strong bond, right? Absolutely, and it is. It absolutely is. The question is, this is a very reactive base, and what you form here is actually pretty stable. Now the question is, why is this stable? Where did these two electrons go? So when this reacted, there was a new lone pair there, right? If I drew the mechanism arrows here, they'd be, right, draw the lone pairs in. These two electrons came here, took these two electrons and went to that carbon. What hybrid orbital are those lone pairs located in? In an sp orbital, right? Everybody see that? This carbon was bonding with using an sp orbital. So where did these electrons necessarily go? They just went to the sp orbital, right? What's the hybrid state of this carbon? Sp, right? How many pi bonds does it have? Still sp, right? So these lone pairs are in an sp orbital. Well, for reference, let's draw an sp3, an sp2, and an sp. If I put a lone pair in each of these, where's that lone pair the happiest and why? So if this is sp3, sp2, sp, where's that lone pair the happiest and why? In sp, why?
Because it's closer to the protons.
And protons, which are in the nucleus, right? Where's the nucleus at? Right in the center, right? Which would be approximately right here, right? So why is it happy? Because these electrons are going to an sp orbital. So this is even though this bond is really stable, is actually pretty reactive. It's kind of a weird way of thinking about it because the product is stable, right? Sometimes things react not because its bonds are reactive. Sometimes things react because they form more stable products. They're able to react that way. So right, the other way around, right? I got done telling you guys, right? Our CH bonds, right? Would these CH bonds be very reactive? No, because what hybrid state is that carbon? Right, and if I put a lone pair in an sp3, that's awful, right? It's not a linear scale here. I guess that's the other thing to think about, right? All of a sudden, going from sp2 to sp is like a big jump, making it stable, right? These two are awful. You're never going to break a CH bond with an sp3 hybridized carbon. In the same way, you're not going to break this CH bond either, right? With this sp2 hybridized carbon, because even though it's better than sp3, right? Is it as good as sp? No. But there's a big jump from sp2 to sp, like a big jump, like a quantum leap. Like all of a sudden this is way okay. Not okay, not okay, okay. Now you still need to have a pretty strong reactive base here to make this happen, but these will not react like that because of hybridization states.